So now I'm going to calculate correlations, but as I go, I'm going to do two things along the way. So first, we're going to do correlations of inflation series. So we're going to make the inflation series out of some CPI data that we've been working with. But we're also going to troubleshoot some issues that come up along the way. So the thing about error messages and trouble spots that come up in R is that you can't really teach them in advance. You just have to fix them as they go. And a lot of times your motivation is just to kind of power through it, get it done, and just get to what you were originally working on. But once you figure out how to solve a problem, if you actually work through it and figure out what the issue is, you can actually save time the next time. So we're going to use the data. The inflation data are going to come from the CPI data that I've worked with before when making real growth rates. And we're going to do some things that we're doing in Lab for Economics 346 at Northeastern. So as we calculate the correlations, we're going to fix some errors. I'm also going to talk about different types of data. Right? So first, we're going to load the data, and we are going to read the CSV off the website, and then it's going to load, and we're going to look at the head of the data. We're going to see that we have our original nominal GDP, and then the price levels. And we're going to see that these are going to rise toward 100 probably around 2010. These are in national currency, and we've worked with these before. But we don't need the nominal GDP. We just need the prices. So we are going to select columns 2 through 5 and delete them. So notice the notation. We take data, and for all rows, columns 2 through 5, the negative means get rid of it, and we're going to name it the original name. And that's just going to change what data is. And then we're going to look at the head. We're going to look at the tail. And then we're going to have just the year, which is column 1, and then 6 through 9. 6, 7, 8, 9. Yes. And so you can see that this starts in 2012 at the tail, and we've already passed the base year because it's higher than 100. But it looks good. And we're going to make inflation from that. Now, if we try what we did in the growth rate series, it's not going to work, right? And that's an issue that came up before. It says non-numeric argument to binary operator. So this is the error message. It gives you a hint as to what to do. But we're going to do two ways to kind of get rid of this. The first way to do it is just to see if maybe the set didn't work. Just try one column and it's going to work. And you can see it looks like good inflation rates. Remember, this is log differences. So we take data of the column, take the natural log, and then difference that. We're going to subtract 1970 minus 1969 and so forth. And because that's going to be in decimals, we turn it into percentages multiplying by 100. And we do that 4 times. Notice I had to copy this, paste, change the number. If I had 100 of these, it would take forever. So obviously it's going to be much easier to fix the problem at the cause and then just kind of go from there rather than doing it manually. But if I do this 4 times, you can see here, I have them. They all look good. I'm going to make inflation, and I'm going to make a series called inf. And you can see here it starts in 1970. We lost one observation because it's a difference, but it looks like plausible inflation numbers, and it's got all the things we need, and we are ready to go with this series set called inf. All right, but the better way to do it is to look at the error and fix. So I saw the word numeric. Now, data can come in different classifications, right? There can be characters, which is for text. Logical is going to be a true-false statement that we'll see next. Factors is based on levels of data, lists, all sorts of stuff. So I'm going to say, well, maybe the data aren't numeric. Some software actually read numbers as text, right? And so we'll see, well, maybe it comes in, it's not reading it as a number, it can't calculate. But the true-false statement, it's asking, is it numeric? And the answer is yes. So that's not an issue for one. And it's actually not an issue for any of them. So these data are fine in this sense, right? So that's kind of a dead end. I'm going to kind of see maybe there's another problem. But before I do that, here's a logical statement. So again, you can have true-false data. This is asking, are these numbers a true-false statement? And it says false. In other words, are these true-false? No, because they're numbers. So this is a way to check the type of data you have. Right. Another thing besides the actual type of data in the cells is the arrangement of the data. So you can have vectors, which have one row or one column, matrices, which we know from math, but R tends to use data frames a lot, which is just their one way it's often used to arrange data. It's kind of similar to a matrix, but we'll see that it is not in this case. So I'm going to ask, all right, is data, all right, so I'm going to make this data here, data 2 is as a matrix. Actually, before I do that, let me ask these questions. Data 2, all right, just data column 2, excuse me, is the second column of data. And I'm going to ask, is it a vector? True. All right. You say, well, what about all these vectors? Are they a matrix? And the answer is false. And that's actually the problem we ran against. These are as a data frame, all right, which the difference is not going to work in the data frame, which we're going to have to fix. So I'm going to take something called data 2. I'm actually going to make a new object. I'm going to say take data. As matrix means turn it into a matrix, make it as a matrix. So I make a new thing, And it is pretty similar, but you can see up here that they're slightly different, and we'll see that they're arranged differently. Now I'll ask, is matrix? Yes, it is, because I just made it as a matrix. So now if I run my form, I'm going to call it inf2. You can see now it calculates. You can see over here that these are going to be fairly similar. This has one more column because I didn't put years on it, but that's the only difference, right? So now if I look at the heads, right, these you can see here 10.15, 10.15, these are the same, right? They in fact, they're both the same arrangement of data. All right, because I made one and it came through as a matrix, and then the next one I made into a matrix. But the original data are going to look different. Right? And so here you have the matrix array, right, which has one row, first row, all columns, and so forth. The data frame does not have that. So it looks slightly different, even though the data inside are pretty much the same. Right? And we can test, are they equal? If I subtract them, the difference should be 0, but remember, one has an extra column, one does not. So the inflation do, but the prices don't. Or excuse me, the inflation does not, but the prices do. And so I have to kind of get rid of that first column. I'm just going to say keep 2 through 5, which means omit 1. Right? I could put -1, but the other way to do it is to tell me what to keep. If I subtract these two, I have all 0. So that means they are the same. Right? Now to the main point of this exercise, which is to calculate correlation. So I'm going to do correlation of the inflation series. And you can see here, these are all fairly highly correlated. Now, if you know correlations, remember that this diagonal column is every variable with itself. So Canadian inflation is perfectly correlated with itself. Right? And then you can see they're pretty high. They're close to 1. Now, this column is actually time. And so we don't really care about if time is correlated with inflation because there's no economic meaning to that. Right? The year goes up by 1 every year. Inflation tends to be dropping for other reasons, but there's no real reason to say that the passage of time is related to inflation independent of other things. So I'm going to say we'll do the correlations for everything except for column 1. In other words, ignore time. You can see that these are fairly highly correlated. Right? Now, because there's so many decimals, there's 8 total digits, I am going to make an object called cores, which is going to round it. So I take correlation of inflation, column 1, and I'm going to round it to 3 decimal places. Remember, I have to call back the object. And here, you can see here that it is now rounded to 3 places. Okay. Now I mentioned that this is the Pearson correlation coefficient. It's pretty much the typical one taught in classes. There's one called the Spearman correlation. If you've ever studied nonparametric statistics, it actually incorporates a lot of rank ordering. And because ranking is independent of outliers, a lot of times you'll find that these are sometimes lower because they ignore those outliers. All right, so I'm going to make cores 2, which does the exact same thing, but there's an extra little parameter here. Method equals, and it's in quotes, Spearman. And then that's the only difference here. It says, change it, instead of doing Pearson, do Spearman. And notice these are pretty high, 0.7, 0.8, 0.9. If you run it here, you can see that it's lower. It's 0.6, 0.7, 0.8. So because the outliers are ignored, remember, high numbers are ranked the same. 1, 2, 3, and 1 to a million are all ranked in the same order. So that's kind of one of the driving forces behind nonparametric statistics. Now, one question for class, there's another command or another type of correlation that can be pulled through the parameter. Kendall's tau is another nonparametric method. You can type in Kendall here, that'll do it. And then for a more challenging question, replace one observation with a huge number and see what happens. So in this case, I randomly chose Japan's 1992 inflation rate, turn it to 2,000. So instead of like 4% or 2% or whatever it is, make it 2,000. So that'll be one way to show what happens when you introduce an outlier. Now, a couple more things. If you ever do a stats table, you'll realize that these are often blank, that you only report the top, usually the top, sometimes the bottom, but I prefer the top triangle because these are symmetric. UK Japan is the same as Japan UK. So you delete these redundant parameters. And so one way to do it is try this lower triangle thing. So if you look at the lower triangle for correlations, you'll see that the lower triangle is true because it is the lower triangle, but the one that's not the lower triangle is false. So this is a logical statement. And so the next thing I can do is I can look at, take cores, which is the correlations, and then say within this, whatever the lower triangle of cores is equal to true, take these true statements and replace them with nothing. Okay, so in quotes is nothing. And now if I call this back, I get cores. And this here, it's a little ugly, and I'll fix that next, but you could see here that this is eliminated that lower triangle. I can get rid of cores with no quote, or get rid of the quotes with no quote. You see it's blank, and then that can be used further. It's easier than sometimes people manually delete these. All right, one last tip. These are time series, and I haven't gotten into time series yet, but let's try a time series plot to see what inflation looks like. So this is how you plot anything in R. I'm plotting this as L for line. And notice the parameters, plot, and what do I call? What to plot? There's two axes. This is actually the X and the Y. So time was here, and then the Canadian inflation is here. Make it a line graph. This is the X label, so the horizontal axis is going to be nothing. The vertical axis is this here. We'll go into this in much more detail later, but if I plot it, it starts to look like a time series. And so this is what Canadian inflation looks like. It's obviously fallen since the 1980s. Right, so this is what we did. First of all, the main goal was to do correlations of inflation. We made inflation, but we solved some problems along the way. We talked about types of data. We talked about classes of data. And then we talked about how that might affect what calculations we can do. So we fixed the problem by making a matrix instead of a data frame. We calculated inflation, then we did Pearson and Spearman correlations, and we got to see the differences between the two. I'll leave Kendall to you, the Kendall's tau to you. And then we also talked a little bit about trying to use a logical statement to make the correlation matrix look better, and then I plotted a time series.